Hello and welcome to our senior project presentation. This is for UAV Quadcopter. This is graduating class of spring 2021, and the presenters and participants in this project are Chad Ryan, Corey Shop, Peter Tiet, and Liam Yerkin. For a quick overview of the project, we are going to discuss everything that comes together to create our UAV quadcopter. This includes a Raspberry Pi, the Python program that runs on the Raspberry Pi, how we power the motors, ESCs, the Pi, the ESCs themselves, the brushless motors, and the PWM signals to control both ESCs and DC brushless motors. And then we'll talk about the MPU 6050 gyrometer, accelerometer, and temperature sensor. Then we'll go into the printed circuit board designed for this project. We call it the D-Pi. We have the R-Pi as in the Raspberry Pi, and we also have the D-Pi, the digital power interface electronics board. And then finally we'll talk about the tests and results of the project.
My name is Corey Shop. I am a senior here at Cal Poly Pomona. I am currently studying electrical engineering and will be graduating with my bachelor's degree in electrical engineering this May. For this portion, I will be covering the Raspberry Pi 4, the MPU 6050, and the ESCs for the quadcopter. The microcomputer that was chosen for the quadcopter was the Raspberry Pi 4. The reason why the Pi 4 was selected is mainly because of that it is capable of supporting Python code and supporting the code for the ESCs on the fly. The Pi 4 is capable of using an SSH. SSH, or Secure Shell, is an encrypted networking technology that allows a user to manage the Pi from a command line over a network connection. When being used in SSH, a terminal session in the command line could be opened and allowed the sharing of data. It was in this terminal that the Python code was written for the quadcopter. Another feature of the Pi 4 is the capability to operate in headless mode. Headless mode is when the Pi wirelessly communicates from peer to peer. This was beneficial for the project because this allowed for the transferring of data without needing a wired connection. It was also beneficial because it was easy to integrate with the Pi on and off of the quadcopter. This means that the configuration of the Pi could be similar to when the Pi was attached to the quadcopter itself. The accelerometer and gyroscope that was selected for the quadcopter was the MPU 6050. The MPU is a 6-axis motion tracking device. The purpose of the MPU is to measure acceleration, velocity, orientation, and displacement of the quadcopter. Inside the quadcopter, there are ESCs, or electronic speed controllers, that connect the Raspberry Pi to the motors. By connecting the flight controller to the motors, the ESC allows the controller to control and adjust the speed of the motors. The ESC that was selected for this project was the Speedix IS30 24S BL Heli S D-Shot 600 30 amp ESC.
To control our UAV, we used pulse width modulation methods, PWM, to control our ESCs and therefore our motors. To instantiate our I/O to generate PWM signals to control the ESCs, we used open source Python libraries, more specifically the general purpose input-output library, the GPIO library. The Pi 4 has multiple pins that can be used as general purpose input and outputs. The pins we used, as you can see on this slide, were pins 11, 16, 22, and 37. These were primed as software PWM outputs according to Python coding language methods, as seen below in the code snippets. They are instantiated with a frequency value of 590 Hz for each pin. Next, they are instantiated with their duty cycle 54%. .start command is used to output a PWM signal from each of the pins respectively. However, for ESCs, the Pi's PWM GPIO pin output voltage of 3.3 volts was not enough to drive the MOSFETs in the ESC. To remedy this, we created an active amplifier circuit using an op-amp. The op-amp, specifically the OP284 ESZ, was set up in a standard non-inverting amplifier setup where the gain G of the circuit is controlled by its resistive values R1 and R2, as you can see. Using a 6.04K resistor for R1 and a 3K resistor for R2, thus giving us a 1.5 gain according to the equation, as shown. After passing the amplifier, the Pi's PWM signal was boosted from 3.3 volts to approximately 5 volts. This voltage was now enough to drive the MOSFET's gates in the ESCs. Therefore, PWM's voltage is now sufficient to control the MOSFETs that control the current flowing into the windings of the motors. This in turn controlling the RPM of the motors as determined by the frequency of the PWM signals in the Pi's master code. This allows for fine motor control. Now showing is the schematic of the PWM amplifier circuit as it appears in the DPi PCB. To power the Raspberry Pi and other components while in flight, a battery was needed, as it is UAV. The battery that was selected was a Yom 4S LiPo 6500 mAh battery. This battery provided power to all the onboard components, most importantly the ESCs, which require high amperage in comparison to other components. However, the maximum input voltage allowed to the Pi 4 is 5 volts, so a voltage regulator was needed to step down the operating voltage for the Pi. This was implemented by a voltage regulator integrated circuit component. This regulator takes in a maximum voltage of 17 volts, in our case approximately 15 volts from the battery, and steps down the voltage to 5 volts at 1.5 amps. This output is now the correct voltage and sufficient amperage for the power needs of the Pi in operation.
Hello, my name is Peter T. and I'm an undergraduate electrical engineering student at Cal Poly Pomona, graduating in spring 2021. I will be talking about the selection of the drum motor and propellers. The motor that is selected is the BR2216 motor. The motor is a 810 kilovolt brushless DC motor. The specs include the height of 45 mm, width of 27.7 mm, weight of about 66 grams, and operation voltage at 7.4 to 14.8 volts. It comes with two clockwise motors that is marked with a red cap and a counterclockwise motor which is marked with a black cap. Inside the BR2216 motor has a stator and rotor. The stator consists of coils wrapped around poles leading to the rotor. The rotor is a permanent magnet with two magnetizing poles. Once current is applied, the coil will generate a magnetic field that will reach the rotor permanent magnet. If the coils are activated one after, the rotor will keep rotating due to the phase interaction between the magnet and electromagnetic magnet. In this case, the stator coil will act as the opposite magnetic pole. As the magnet on the rotor, this will pull the magnet to the stator direction and will repeat for the other stators in the motor, creating the rotation. The current waveform displays the truth table in order to ensure that the motor can rotate continuously. Because of this, each phase do not share the same polarity, so the rotor will continue moving to its opposite magnetizing pole. Between the positive and negative current polarity, the motors will shut off momentarily to ensure that the polarity do not interfere with each other. This picture is the example of the simultaneous movement of the rotor due to the changes of coil polarity. The reason why the BR2216 motor is selected is because it is light and efficient. The motor can be controlled while during operation and can be controlled by an electronic speed control, so that the motor will always be running at the appropriate speed. It has high durability because it does not have brushes and a commutator that will wear down due to continuous moving contacts. Lastly, The brushless motor is the most efficient motor for devices that runs continuously. In this picture, the positions of the motors are shown. The clockwise motors are placed at the top right and bottom left, and the counterclockwise motors are placed at the top left and bottom right of the frame. The reason why the clockwise and counterclockwise motors are placed diagonally is to only give the vertical acceleration at uniform RPM. Across all motors, the configuration negated all the undesired vectors of acceleration at a hover. Here is the motor's schematic. Here is the datasheet of the motor. Here is the motor's characteristic along with the data for each corresponding voltage. The motor that we have is 810 kilovolts, which is spec store right here. Now to the selection of the propellers. The way Cork 10-inch Quadcopter performance propellers are selected. The selection of the propellers is based on 5 main variables: the size, pitch, blade configuration, material, and shape. The figure is shown below is the selected drone propellers. Each variable selection will be discussed in detail. The propeller is 10 inches, which is relatively larger compared to the other drone propellers. The size of the propellers is directly correlated to thrust, responsiveness, and balance that the drone will have in the air. The larger propeller will sweep through more air but will take more energy to get it spinning and will respond slower to a motor input. The main benefits of a larger propeller are increased thrust, better stability while hovering, and more control when making changes to the direction. The propeller has a high pitch with a 4.5 shaft diameter. A higher pitch results in an increased thrust and top end speed, but less torque. Additionally, the propeller will respond to the motor input slower, use more power, and is more efficient when the drone is moving relatively quickly. While the 5 shaft diameter is considered a high-pitched propeller, the 4.5 shaft diameter provides a good blend of responsiveness and speed. Blade configuration is one of the most important factors in selecting the propeller. The blade configuration refers to the number of individual blades on the propeller. The blade configuration of the selected propeller is a 2-bladed propeller. Picking a 2-bladed propeller are the most effective because only 2 blades are creating drag and provides flight balance. Also, increasing the number of blades is not efficient as increasing the propeller size, which is the reason why the selected propellers are larger compared to the average size. The material of the propeller is plastic. Plastic blades is stiff for their weight and allows the propeller to maintain shape regardless of how fast it is moving or changing direction. If the drone were to crash, the propellers would be durable enough to withstand a collision. The shape of the propeller is determined to the amount of thrust and drag for the drone. The bigger surface area of the propeller will generate more thrust, but create more drag and consume more power. The shape of the selected propeller is a hybrid bill nose. The hybrid bill nose is the most effective shape because it has more surface area but generates less thrust. In the picture, both common propeller shapes are shown. The hybrid bill nose is at the top while the bill nose is at the bottom.
Hello, my name is Chad Ryan. I'm currently a 4th year electrical engineering student at Cal Poly Pomona, and I am also a full-time intern at Jet Propulsion Laboratory working on a project called Lunar Flashlight. For this project, the UAV Quadcopter, I decided to design and build a printed circuit board to not only partially be a chassis for the drone, but also to kind of help support the Raspberry Pi. And you'll see what I mean by support, I guess both functionally and physically supporting it. So let's start small. Let's start with the schematic documents. So here we just have a voltage regulator, that L494 0D2 T5. This voltage regulator takes our battery voltage, which ranges anywhere between, I would say, 11 to 16 volts, and outputs a nice 5 volts for our Raspberry Pi to use. That is the operating voltage of the Raspberry Pi, which is why we chose a voltage regulator that outputs 5 volts with an input range acceptable for our battery. Now I placed 2 capacitors on the input and output here, kind of as low pass filters. You don't see any resistors there. This is of course because we don't, we're not actually applying a low pass filter. You could just almost think of these as low pass filters. So what these capacitors do is they just smooth out the signal. If you have any noise or increase or decrease short term in battery voltage or our output voltage, the capacitor will try to limit us from going above 5 volts, and it will also try to limit us from going below 5 volts or our battery voltage. And the reason for having 2 different values in parallel on each side isn't to increase capacitance. This is more of to broaden the frequency response of any noise or dips of varying frequencies that may have a small effect on the performance of our system. So that's why we have a 0.1 microfarad and a 1 microfarad capacitor in parallel on the input and output. It really just widens that block range to remove lower and higher frequencies that we do not want, as these are both DC signals. Alright, now to move on to the PWM signal amplifiers. So we have 4 of these amplifiers. I'll zoom in on one just to make it easier to see. So the purpose of these amplifiers is to take our 3.3 volt PWM generated from our Raspberry Pi and amplify it to an amplitude that drives the ESCs we're using. The ESCs we're using operate off of a 5 volt PWM signal along with DC battery voltage power. So if you were to drive 3.3 volt PWM, you wouldn't really see much at all. I believe we tried this and we saw a little bit of spin, but I think it was apparent that we weren't going to fully drive any of the MOSFETs. I think they were severely limited inside of the ESC because of this 3.3 volts on the gates rather than having a full 5 volt on the gates of the MOSFETs. And we have 2 resistor values here. We have a 3K right here, the ERA8R1 component. We also have a 6.04K resistor for R3. This is just a gain of 1.5 to take our 3.3 to 5 volts. I think it's actually slightly higher than 1.5. And we chose this 6.04K value not only because it's a common component, but just from simulation we tried adjusting values a little bit and we saw a little bit more clear and higher output from the OP284 while doing this. So if we check the other PWMs, they are identical. You will see U1A and U1B for the 2 different OP284s, and then U2A and U2B. This is because U1A and U1B, for example, they're within the same 8-pin SOIC package. And that's why they call it the OP284, because there are 2 84 amplifiers inside of this package. If you look at the OP184, you will also see the same thing. And we chose this because it was just easier for this application. It's really no benefit or cons of switching between the 184, 284, or 484. This is just because we had some spares and it kind of helped with the physical design of our board. And once again, you see the 0.1 microfarad capacitor here. You see a 1 farad or 1 microfarad capacitor here, for the same reason as mentioned with the voltage regulator. Alright, so now I'll move on to the MPU 6050. This is a gyrometer, accelerometer, and digital temperature sensor all wrapped in together in one IC. What you see here is just multiple pull-up resistors, pull-down resistors, and then once again capacitors, not only to smooth out noise, but also to help this IC operate. You'll see some ICs, you don't need any external components for them to operate. Most of them you do. For example, the resistors on the OP284s we just had. In this device, it uses I2C to communicate with the Raspberry Pi. You can see our SCL and SDA lines over here. And we actually did not need to include the interrupt and the AD0 signals, but I did just in case we would ever find a use for them, and they're not being used. Currently in the design, the interrupt is pulled low to ground. We just short it to ground. And the AD0 is actually connected to 3.3 volts. Now this was a design change. In the board you still have this pull down resistor here, but out where AD0 comes this direction, it's shorted to 3.3 volts. And that allows us to communicate with the MPU 6050 and get gyrometer, accelerometer, and temperature telemetry. Alright, now for the printed circuit board. So here's the 3D layout of our board. There's really not a lot of components on here. Before I dig into the placement of the components and the design of the components, I want to first touch on all the mounting holes you see here. So you see these two groups of mounting holes with these larger pads here on each corner of the drone. So these two holes on each corner are for mounting onto the arms of the drone. There are 4 arms of the drone, so we have 4 pairs of 2. We have these large solder pads here to supply battery voltage to the ESCs. If I go into 2D mode, you can see that, yeah. Analog ground, B battery. In this board, I actually designed it to do both functions, not just the digital and analog amplification of the Pi, but also to be the power board. And the reason why we have 2 boards is because the arms are attached to a board on the top of the arms and then the bottom of the arms. So rather than designing 2 separate boards for this, I decided to integrate them into one board and just to order multiple copies. That way it's cost effective, it's more efficient with design time, and I also just wanted to try that out because this board did not have much to it in the first place, so I didn't see any harm in adding more components and making it more functional than it was, all on its own. So that explains why we see these solder pads and these mounting holes and these PWM signal outputs here, which I will touch on more in a moment. So for the PWM outputs, the amplifier circuits, I wanted to use polygon pores for power, just to allow power to move more freely against the IC. Past that, I tried to stick with larger components on the board. I did use some smaller components, like here the 0402 capacitor, and that's just to make it easier to solder on. And if you follow the outputs here, we have analog ground coming here. You also have the 5 volt amplified PWM signal coming here out of R1. You see, it's a pair that goes out towards the edge of the board, where we then have a pigtailed connector to the ESCs. And you see this on each corner along with the analog ground and battery voltage. Now these are the 4 inputs to the ESCs. Analog ground, battery voltage, and we have a ground for our PWM. In this case, it's still analog ground. We have net R5 too, which is one of the PWM outputs. Net R1 too, another PWM output. And we have the same case for the bottom left and right of the board. And this PWM amplifier circuit is identical, it's just flipped, just to allow for the flipped orientation of the board. Now for the voltage regulator, I used a larger polygon pore here just because we're applying a large voltage to this voltage regulator. You could see the capacitors that I mentioned earlier to smooth out our DC signals. You can see these two pads here. These are where the battery mounts. I made them larger, not just because the battery leads are large. I think they're 16 gauge wire, but also because there's a lot of current moving through them, and we need more cross-sectional area with more current. And here we have the output 5 volt. This 5 volt goes to a pigtailed USB-C connector, which is then eventually plugged into the Raspberry Pi. So that connector, the USB-C cable, was just cut and stripped, and then we took the ground cable, we took the power cable, and we soldered them onto these pads accordingly. And then these mounting holes in the middle, these mounting holes are actually where the Raspberry Pi is mounted. We have standoffs on the board. The Pi rests on top of the standoffs, and they are screwed in. From here, the Pi is connected to these solder pads with just twisted pairs Teflon wires. I chose Teflon just because it's stronger, and this drone will be moving around quite a bit, so I don't want any wires to break. Also, say if a propeller hits a wire, it's a weaker wire, a weaker insulator around that wire, it could easily break, and I don't want to expose any power or grounds or any signal to a short circuit. And to move on, I talk about this component last because it does function. We do get Excel, gyro, and temperature telemetry onto our Pi, but we just simply ran out of time to implement it and integrate it into our code. It ended up being quite a challenge on its own, but compared with the time constraint we had by the time these boards were delivered, we had problems getting it to function. But nonetheless, it still works. So you see our pull up and pull down resistors, you see our capacitors there to smooth out noise. We have our 4 pins that go to our Pi. These are all soldered directly onto the GPIOs of the Pi. And the last thing to touch on this board is the layers of the board. Go into 3D mode, panels, view configuration. Increase the thickness, and now we could see kind of how this board is connected with its layers. Now the layers on this board were purely reserved for power planes, meaning we don't have any tracks or polygon pores on these layers. We just have vias connecting power signals from the top solder of the board to different layers. And we could see that if I select any of these, we could see where they're connected. So this is our battery voltage here. I switch to ground. Here's our ground signal. Rest towards the top. Choose our 5 volt signal. Rest towards the bottom. That concludes the walkthrough through our printed circuit board we designed. After populating, building, and testing this board, we found that it works, which is fantastic. The PWM amplifiers work, the MPU works, the voltage regulator works, the design works, which is very good news, especially when this Raspberry Pi 4 relied on extra support equipment to control the ESDs. We need these PWM amplifiers for this drone to work, and that was a big part of this circuit board. Thank you. That will conclude the printed circuit board section of this presentation. So now let's dive into this, the Python program section of this presentation. We're using a few libraries here, the RPi GPIO library, that's for PWM outputs. We're using the time library. Now we have some prerequisites before we start driving our PWMs and changing them as desired. And I will mostly mention the frequency we choose. I won't focus on how to generate PWM on a Pi, but I'll focus on how we use Python programming on a Raspberry Pi to get us where we need it to be. So you see right here we have a frequency of 590 Hertz on every motor, and notice this is the first frequency that we send to the ESCs. And this is important. The ESCs, how they work is when they're first turned on, that first PWM signal they receive, it takes the signal and it basically tells the ESC what is going to happen next. What are we going to do with this signal? And this is our lowest motor speed. 590 Hertz gives us our lowest motor speed. Increasing in frequency will slow down the motors to a halt. Decreasing frequency will speed up the motors, so it's an inverse relationship. So sending this 590 Hz PWM signal to each ESC will initialize them and calibrate them to work within this range. And that's how these ESCs work with drone motors especially, is, you know, if you want to use a different motor, you don't necessarily have to buy a different ESC. You could rather send in a different initial signal, and that could be changed with ECE or frequency. Through trial and error, we found that starting at different duty cycles and starting at different combinations of frequencies along with these duty cycles would calibrate the ESCs differently. I had the realization we should focus on lower frequencies because the Pi uses software-generated PWM signals, not hardware-generated PWM signals. And with software-generated signals, you kind of start to lose performance towards higher frequencies. You need to rely on a clock, as it's a software-generated PWM output. So we started digging through lower frequencies combinations with duty cycles, and we found that this initializes the ESCs in a way to where we have a broad range of duty cycles and frequency ranges to change our motor speeds. And if you look here, we have some options here. The only input is an integer input assigned to variable A. Depending on your integer input, you could either remotely change the duty cycle of all the motors by 1%, or you could remotely, uniformly change the frequency of all motors at once. You could decrease frequency to increase motor speed of all 4 at once. You could increase frequency of all motors of all frequencies to decrease motor speed, or you could go individually. So as you can see, this is not necessarily a final version of a Python program you would actually find on a drone somewhere. This is much more of just an easy interface for us to use while testing the drone. And as you'll see later, our drone does not necessarily hover, and you cannot necessarily fly it for more than a few seconds. So the code kind of keeps up with the performance of the drone. And that will wrap up the Python section of this presentation. Alright, so after adding these offset frequencies later on in the code, after the ESCs were initialized with the 590 Hz PWM signals at a duty cycle of 54%, we get slightly better performance with the drone. Rather than instantly toppling over, we get some lift, and we also have some spin, which tells us that not all the motors are spinning at the same speed at the same time. So I'll play this video, and we could see the difference in performance just by applying offsets to our initial, well, I would say not initial, but our post-calibration initial frequency values for PWM. So as you can see, the drone did not necessarily float, but rather than toppling over, it has more air time. Previously, I think all arms were not off the ground. I think we had 1 or 2 on the ground, and you just see the drone kind of flip over. After adding some offsets to our frequency values, you see it kind of it lifts much more. We'll play it again. The lift time drastically improves from maybe even 0 to 4 or 5 seconds. And that concludes the testing portion of our presentation. We hope you enjoyed this senior project presentation, and we hope that this information helps anybody who pursues this type of project in the future, whether it is Raspberry Pi integration, printed circuit board design, or ESC and DC brushless motor use. Thank you.